Thank you, ma'am.
Mr. Anup, you can take over.
Yeah. Thank you so much.
Yeah,
Right.
thank you.
I'll just switch on my video so you can see me. Hi, everyone. Um, like ma'am pointed out, today I'm going to do a small presentation to all of you on waste to energy
Mr. Anup,
concepts.
excuse me.
Yes.
We are not able
Thank
to
you, ma'am.
Mr. Anup, you can take over presentation.
Thank you so
I think
much.
your video is not on. Yeah,
Right.
thank you.
I'll just switch
Yeah,
on
that's
my
fine.
screen right now. Video so you can see my screen. Hi everyone. The presentation which I prepared for this. Like ma'am pointed out, today I'm going to do a small presentation to all of you on waste to energy
Mr. Anup,
concepts.
excuse me. Yes, yes.
Yes.
We are not able
Thank
to
you, ma'am.
Mr. Anup,
So,
you can take over
yeah,
presentation.
I've prepared this
I think your
presentation
video
for the
is
students
not
of
on.
Hindusthan College of
Yeah,
Engineering
thank
and
you.
Technology,
Yeah, that's
so
fine.
that they can understand what is video, so everyone can see
what
my
is the
screen.
elements
Hi
of a
everyone.
waste to
The
energy
presentation
plan
which I prepared for this. Like
and
ma'am pointed
what
out,
is the
today I'm going to do a
relevance
small
in
presentation to
diverting
all of
waste
you
away from
on
landfill?
waste to energy
Mr. Anup,
So
concepts.
I
excuse
kept
me.
it a bit
Yes,
technical.
yes. We are
For
not
the
able to
ma'am.
Mr.
engineers,
Anup,
but not
you
too
can take
technical,
over
so that I
presentation.
can convey the
I think your
presentation
video
for the
is
students
not
of
on.
Hindusthan College of
Yeah,
Engineering
thank
and
you.
Technology. I'll just
Yeah,
switch on
that's
my
fine.
so that they can
I'm going to
understand
start
what is
video so everyone can see
what
my
is the
screen.
elements
Hi
of a
everyone.
waste to
The
energy
presentation
plan
which I prepared for this. Like ma'am
and
pointed
what's
out,
the
today I'm going to do a
relevance
small
in
presentation
diverting
to all of
waste
you
away from
on
landfill?
waste to energy
Mr. Anup,
So
concepts.
I
excuse
kept
me.
it a bit
Yes,
technical.
yes.
What are the
We are not
issues?
able
Thank
to
you, ma'am.
Mr.
So
Anup,
not
you
too
can take
technical,
over
so that I can
presentation.
convey the
I think your
presentation
video
for the
is
students
not
of
on.
Hindustan.
My friends, they asked me, what is the difference between a dump site and a landfill? That's when I realized that, like you need to also educate the public what is the difference between a dump site and landfill and why it's different. So, what's the difference between a dump site and landfill? On the left side, you can see a dump site, which used to be a Norman, but now most of them are closed. My friends, and on the right hand side, you can see a dump site. What is the difference between a dump? You spot any difference? Not really. It's all the same. So it's limited land space. That's when I realized that like no tree. You need to also educate the public what is the difference because the space is limited and why it's so the whole point of putting it on fire is to utilize the space for more waste. So it's resulted in extreme levels of toxic gases. On the left side, you can see a dump site, and which used to be an and most of them are closed. People in the nearby neighborhood, my friends, have, and on the right hand side, you can see a dump site. What is the difference? And also, these kind of practices also lead to not really contamination of the groundwater. So it's limited land space. So this is that's when I realized that like no tree. You need to also educate the public what is the difference because the space is limited and why it's so the whole point of putting it on fire is to what is it utilize the space for more waste. So this is a picture of resulting in extreme levels of toxic gases. On the left side, you can see a dump site, and which used to be so you can see entrenched. Most of them are closed. People in the nearby neighborhood site of the trenches is covered with the dump site. What is the difference? And also these kind of practices also lead to not really contamination of the groundwater. Also limited land space. That's when I realized that like no tree. We need to also educate the public what is the difference because the space is limited and why it tends to contaminate the groundwater. So to prevent is to what is the utilize the space for more waste. This is a picture of results in levels of flares. On the left side, you can see a dump site, and which used to be a most of them are closed. Nearby the site and have trenches right soil, you can see a dump site. What we did, we also fixed a water layer when the not waste contamination of the ground was landfill gas limited to land space. That's when I realized that a lot of micro need to distribute, but what tends to happen in landfill is tends to contaminate the groundwater. So to prevent that process of acting on waste land space more waste, this is a picture of results in levels of flares. On the left side, you can see a dump site, and which used to be a most of them are closed. Nearby the site and have trenches right soil, you can see a dump site. What we did, we also fixed a water layer when the not waste contamination of the ground was landfill gas limited to land space. That's when I realized that a lot of micro need to distribute, but what tends to happen in landfill tends to contaminate the groundwater. So to prevent that process of acting on waste land space more waste, this is a picture of results in levels of flares. On the left side, you can see a dump site, and which used to be a most of them are closed. Nearby the site and have trenches right soil, you can see a dump site. What we did, we also fixed a water layer when this contamination of the ground was landfill gas limited to land. That's when I realized that a lot of micro need to distribute, but what tends to happen in landfill tends to contaminate the groundwater. So to prevent that process of acting on waste land space more waste, this is a picture of results in levels of flares. On the left side, you can see a dump site, and which used to be a most of them are closed. Nearby the site and have trenches right soil, you can see a dump site. Captured. So this is an example of how we strategically place uh, landfill gas capture wells across the landfill, and it's usually flared. So why do you want to do flaring? So like I mentioned earlier, the landfill gas is majority methane. So methane, as you might know, it's a greenhouse gas, and it's 25 times more potent than carbon dioxide. So right now we are discussing about climate change and controlling the greenhouse gas emissions. So you need to flare it to prevent the contribution of your country towards greenhouse gas reduction potential and commitments. So that's one of the reasons why I install these flaring units. So is flaring the only option? Not really. You can see in certain countries, they also try to recover energy from these landfill gases. So on your left-hand side, that's a typical landfill gas generation graph. What happens is during the initial phase of the landfill, so in Oman, for example, it takes 5 years for the landfill to be completely full. So once it's full, we cap it with a, like I mentioned, that those layers, with the LDP, HDP, geotextiles, and all that, we cap it and we close the landfill. And from the gas wells, which are strategically located, we capture this gas. So what tend to happen is during the initial few years, once the landfill is closed, again, the landfill gas generation, the volume of methane generated is very high during the initial phases. Why is that? It's because food waste and other readily biodegradable waste starts degrading much faster, and it produces methane. So that's why the peak is very high during the initial phase. It's indicating that all the food waste in the waste is being digested by the bacteria. But then over a period of time, it reduces because there's not enough food waste in it. But there are still other non-readily degradable waste, like for example, wood or textiles. You know that it disintegrates, but it's not so fast as a food waste to disintegrate. So that starts degrading. So the landfill gas tend to drop with time. So like after 40, 50 years, there's no more gas generated from this particular landfill. So when you plan to recover energy from a landfill, this is what you do. So that orange box, power extractor, that's usually or typically that's the span, that's the gas that you can ideally expand by extract for energy recovery. Because when you do investment for extracting energy from landfill, you need an assurance, you need gas supply for 20, 25 years. You cannot build gas recovery and conversion system for just 5 or 10 years. That there's no revenue to be made. So ideally, when you plan the system, they devise it in that way that you can extract some certain amount of gas and you can recover energy from that gas. So on the top right hand corner, you can see some of the systems that are deployed. They use a engine called Yenbacker. It's an Austrian company. They install such engines in a Latin American landfill to extract energy from the landfill gas generated. This is a schematic of the whole system. So the landfill gas recovery system does not go into the fire system because, as I mentioned earlier, it can only take certain amount of gas. So that gas is converted to energy using the gas engine, and the remaining is flared to reduce the greenhouse gas emissions as a result of the methane. So sounds like landfill is a good solution, right? Why can't we all go for it? Not really. Landfill is a long-term liability. Um, we can see how the cells are getting completed uh, on this particular picture. The far end is the new cell, and the one close to us is a new cell that's almost complete. So once it's complete, it looks like a mountain. It can go up to 25, 30 meters. Delhi, I believe it went up to even 50 meters, the height of the landfill itself. So once it's full, you tend to close it and then you start capturing gas. So what is the cost associated with the landfill? There's a lot of cost. There's a cost of designing and construction. There's also the cost associated with the operation of the landfill. But after the closure, like the cell which is you see right now, it's once it's complete, uh, you have to monitor this landfill for another 30 years. And you have to maintain it also for 30 years. So that's a lot of expense for something that has no value. And these are the direct costs, but there's also indirect costs associated with landfills, which is public acceptance. I don't want a landfill next to my house. So it's very difficult for you to find a strategic location to, to develop a landfill. If you see in this picture, there is not even one household near this particular landfill. So it's a very remote area that we identified for developing this landfill. So in India, like you cannot have a landfill next to Coimbatore city. No, like the public will not allow that. So there's an environmental risk associated with these landfills. There's fire risk associated with landfills. There's been cases where landfill, because of the biological activity, fire, the methane emitted caught fire, and then it was a big disaster. So you don't want a landfill again as a long-term solution. And then loss of resources. When you landfill something, you are saying goodbye to that resource. You cannot recover it. So the whole point of us being resource efficient, landfilling is not an option to explore. So it is an option to have as a contingency, but that should not be the solution. So what is the quantity of waste that we're looking at in India? So this is the waste generated on a daily basis across some of the major cities in India. It's a huge volume, but bear in mind this is MSW, only MSW. There is also wastewater and construction which is not accounted for this particular quantity estimation. So this is the volume that we are dealing with. All right. So once you understand the volume, what is in this waste? So there was a report which was published by World Bank back in 2012. It's updated again. There's a new version that came out in 2016. It's called water waste. So it compares the waste composition for different income levels in different types of countries. So they did an extensive study. They went around all continents, and they found out that countries with low income or middle income, they tend to generate more organic waste. Whereas countries with very high income, they tend to generate less organic waste and more recyclable waste. So what is meant by recyclable waste? It's paper, plastic, glass, more packaging waste. So this particular scenario says that what I'm trying to get at here is you need to understand your market for developing a solution. So you understand what is the composition. So what's happening in India? This is an example of the organic waste in two metros in India. And it was a very recent study. It's published in 2020. You can look it up if you want. So on a general basis, for whole Indian metros, the study found out that 41% is biodegradable. So it's food waste, which requires some sort of bioprocessing to handle this particular waste. Whereas in Coimbatore, you can see it's around approximately 60% of the waste SW is organic. Whereas in Bangalore, it's a very high percentage of food waste or biodegradable waste. So that's for metros, municipalities or corporations. What about panchayats? As you know, in India, we have panchayats, we have municipalities, we have corporations. So it's all different because the income level is also different across the municipality, the panchayat, and the metros. So I happened to be part of a team that did a study back in 2016 across four panchayats in Kerala. And the result again shows that at panchayat level, more than 65% of the waste is organic in nature. And it was also helpful for us to understand like how much is the recyclable fraction. Excuse me one second. Right. So best method of handling or treating the waste. So some of you might have seen this particular hierarchy. The best option is okay. So the best method uh, is I'm really sorry. One second. So I'm just getting some disturbance. So the best method is not to have the waste in the first place. Preferred option is landfilling the waste. So you can see there's recycling, there's energy recovery. So there's a lot of options that you can utilize to handle the waste generated. One second. Right. So this is an example of how different countries in European Union handle the municipal waste generated in these countries. So you can see that countries that require energy a lot, like Sweden, Denmark, because of the cold climate over there, they tend to rely mostly on incineration of waste for energy recovery. Whereas countries like Germany, where there's a lot of manufacturing, they tend to rely more on material recovery than energy recovery. So what it shows is each country in European Union itself have different ways of handling the solid waste generated in the country. But regardless, they have set a target that by 2030, at least 65% of the municipal waste should be reused and recycled. So it's 10 years down the line, but still, you can see some countries are almost there or making progress in achieving this particular target. So, what are the drivers for waste diversion? We talked a lot about waste diversion. Why should the country do this? Mostly it's regulation, regulatory requirement, and the European Union have set a landfill ban, or at least a landfill target to reduce landfilling to up to 10% of municipal waste by 2030. There's a landfill tax on top of it, where the waste, if you send the waste to a landfill, you have to pay a tax to the government. India is also making positive progress towards something similar. Uh, Excuse me. So if you're not, can you mute yourself if you're not speaking, please? Okay. Right. So for India, the priority is always to recycle the waste. So the priority set by Indian government is that you have to recycle the waste. Only the non-recyclable waste, which has a calorific value of more than 6.2 megajoules per kilogram, should be sent for a waste to energy plant. Or they also give the option of co-processing it with other fuels in a cement or thermal power plant. They even have an ambitious plan to stop landfilling, but the timeline is depending on the individual respective states to make a decision on when they want to set a landfill ban. In Oman, it's a bit different. So our target is by waste away from landfills. We were not able to do that, but we are making positive progress towards it. We did work on all the feasibility studies. We developed the plan. So there will be a tender coming soon. By 2024, at least we'll be able to reach our target of 60% diversion away from land. Reduce the per capita generation of waste to less than 1 kilogram per person per day. Why is that set before 2040? Because it takes awareness campaigns. So, no, behavioral change. It's not something that you can do overnight or within a year's time. It takes a lot of time. You need to educate the next generation on the importance of waste reduction. So they have set a timeline of 2040 for that particular task. In Austria, although it's in the European Union, you can see they are much ahead of the target set. So they had a ban from 1997 that they will not landfill any waste which has more than 5% total organic carbon. They even have a ban on landfilling of hazardous waste by 2020, 2001. So, you can see that it is up to the countries in European Union to set their own targets and policies in place for diverting the waste away from that. So what's the most preferred option for treating the waste? So this is a very simple graph. There's a picture that will tell you like for food and garden waste, the best option is bioprocessing. So bioprocessing is biogas or composting. There's some of the common examples that you might be aware. Uh, for fractions such as textiles and plastic, and, paper and wood, thermal option is also available. Material recovery option is also available for some of this waste again. But I put a dollar sign next to the material recovery. I'll tell you why exactly that. Ceramics and soil, you can use it as an aggregate recycling recovery. So you tend to use a lot of sub-base for construction. So you don't need to use natural materials or from mines. You can use the waste that we generate for road sub-bases. So that's another option that we can explore. So when it comes to economic recovery, disposal is least option. But what is the truth? The best for the government, from government's perspective, because I'm working in a government sector, so I understand from government perspective what costs you money and what what requires subsidy and what actually can make money. So reuse is the best option. If you can reuse the waste, then that's the best option for the government. Like you don't have any investment, so it's the highest positive value because you're not producing any waste. You don't need to collect that waste in the first place. The government don't have any cost associated with it. The second option is segregation source. So you might know about this multiple bins, and even in Kerala, there's a concept of Kudumbasri coming over to your house to source segregate certain types of waste. So if you source segregate the waste, uh, the option of recycling it is much higher. There is not much cost associated with it because the soon as you collect the waste separately, you bring it to one depot, you source it together, and then you transfer it to the recycler. There's not much investment needed in that particular value chain. If you go to sorting, which is where you mix the waste together, once you mix all the waste together, then there's a cost. You need to sort it. So there should be a line of people sitting or standing and sorting the waste into different fractions. Then you need to clean it. Then you need to decontaminate it. So that costs you money to run such a plant. You need to meet environmental norms, the health and safety aspect of the people who work in such a plant, fire safety associated with storage. So all that comes into play. So it costs you money. And next option is waste to energy. As you know, you're not recovering value for the material, only for energy. And energy, as you know, the cost of energy is reducing as renewable energy is finding more market share in the grid. So waste to energy tends to be not a preferred option over a long period of time because it costs you money. But regardless, it's needed. I'm not saying that you don't need waste to energy. In certain situations, you do need waste to energy. I'll come to that. Then the least option is obviously disposal because there is no value, there's no energy recovery, or there's no material. So that is the least preferred option. So again, coming back to the concept of circular economy, like I'm sure a lot of you must have heard about circular economy, where the country needs to be self-sufficient, self-reliant. It's now the word used by our prime minister. So what do you need to do for such task? You need clean raw materials. So you cannot have a dirty way material recovered from waste and going back to the value chain because again that's not accepted. So always preferred option is reuse and the segregation so you can get cleaner materials which can be sent back into the production process again. So what is the option? What's the solution? The solution is not a straightforward solution. It's an integrated solution that you need. I cannot say I need waste energy and I don't need source segregation. I cannot say I need source segregation and recycling. I don't need waste energy. You need an integrated solution. So obviously the priority is uh, prevention of waste. Second is source segregation. Once you segregate, you can rely on mechanical, biological, thermal, and other treatment options that are available. And third, energy recovery. And finally, the byproducts or rejects from the system can be landed. Um, Obviously, the system needs to depend on the first and the second law of thermodynamics. First law of thermodynamics is energy needs to be balanced. And second is in a very short, in a funny way, what second law of thermodynamics means is you cannot unscramble an egg. So once it's scrambled, it's scrambled. So, and also once you develop a solution, you need to look at the economic decisions. Like you need to look at the long-term cost. So if you don't have, say, if you're relying on landfill or dump sites, that's the least cost option. There's no cost associated with it. But does it capture the full cost? No, it does not. It does not cover for the cost of contamination of the groundwater. It does not cover for the cost of contaminating soil. It does not account for the cost of causing health damages to the. So once you account for all the costs, we'll start looking at a different picture. It's not purely what's the cost right now. It's what's the cost over a period of 20, 25 years. So let me go into the details of bioprocessing. So I've been talking about bioprocessing for some time. I'll just give you an overview what is meant by bioprocessing. So there is two types of bioprocessing, one very common ones. This anaerobic biodigestion or digestion, and there is aerobic digestion. Anaerobic digestion is food or other biodegradable waste is treated by not to be sorry, again I'm getting so so yes, so it's treated in the absence of air. Once it's treated by microorganisms in the absence of air, it generates biogas, which is rich in methane. As you know, methane is a combustible gas. You can combust it using a gas engine, and you can recover heat and electricity from it. The digestate can be stabilized, dewatered, and sent as an organic compost. The different types of stages of biodigestion you can see on the left hand corner. It's hydrolysis, it's acetogenesis, acidogenesis, then acetogenesis, and methanogenesis. So most biogas plants have these four phases, but again, the order and the time of each will differ depending on the technology and the system that you use. And then there is the aerobic digestion, which is composting. Again, in the absence, like unlike the other process, this happens in the presence of oxygen or air. The microorganisms feed on the food. They develop these soil amendments, which you can again use in the farm, produce food again. So it's a circular concept. I'm sorry. Yeah. So this is an example of what biogas looks like. This is something which we are developing here in Oman for taking the food and vegetable market waste, and also from slaughterhouse. We take the waste from these two markets and send them to the biogas plant, which will produce enough electricity. It's co-located next to a university here. It's Sultan Qaboos University. So the waste will generate enough electricity for powering part of the university's requirement. And the university also have a co-located farm and farming community. So they're going to use the digestate for their. So this is another example of the composting and what it looks like. It's different. There are different types of composting. This is one example of windrow compost. It's quite common. You can see that in a lot of countries they adopt the windrow composting method. It's also a static composting. So you get good quality compost. Obviously, it's from organic waste, it's not mixed waste. So this compost can be used for various farming applications. Now moving on to thermal treatment. So thermal treatment, what is included in thermal treatment? Clearing the water all the time. So waste is sent through a thermal treatment process. It's burned, and the result of the burning is you get flue gases, different types of gas. You get bottom ash, and you recover from this process useful energy, which you can use for producing steam, or you can use it for producing electricity. So it's very important to understand the waste component and its characteristics when you go into the raw material. Like for example, if the waste is fully organic, fully food waste, then there is no point in burning this waste because as you can see, the calorific value of the waste is influenced by the individual components. So when you want to burn a waste, the first thing you look for is what is the calorific value of the waste, not the individual components of the waste. So that's why the composition of the waste is very important. But as you can see, food waste have very low calorific value. So that makes no sense to burn food waste. So going back to our initial discussion that we need to do source segregation or divert the food waste away from the other option. But then as you can see, wood waste, paper, textiles, plastic, they tend to have high calorific value. So the more the percentage of these components in the MSW fraction, the more the calorific value of the waste, so the more energy you can recover. So now we're going a bit technical. Again, so those who are interested can listen. Those who are not, can take a short break. So this is a firing diagram. So for an engineer, you're developing a waste energy plant. This is very important. So this helps you decide the size of the plant, the waste energy plant, based on the calorific value and they based on the energy demand. So, for example, uh, the government run electricity grid. They require, say, 65 megawatt of additional capacity. So what we tend to do is once that is fixed, okay, the government tell you I need additional 65 megawatt. What you tend to do is you work backwards, okay? So you test, okay, what is the calorific value? The slope lines, they are the calorific value of the waste. So if my calorific value of the waste is say 9.2 megajoules per kilogram, which is quite high, but in Middle East we tend to see more 9.2 and 11 megajoules, but in India it's mostly 7.7 or below 7.7 because of the moisture content. But anyway, I'll take the example of Middle East. So 9.2 megajoules per kilogram. So you know the energy, the thermal input, because that's kind of fixed. So now what you tend to do is, okay, if the calorific value for the waste is 9.2, how much should be the waste throughput? So you can see for, like for example, I'm taking 328 gigajoules per hour. So for that particular waste, you need to be feeding around approximately 36 tons per hour of that particular waste. So this kind of explains the capacity planning of the plant based on the calorific value and the energy demand. So all three are interlinked. So what are the examples that you have across the globe? So in Europe, there are around 500 installations of waste to energy. In Scandinavia, I mean, there's a good example. You can see that picture on the bottom right corner. It's a plant in Denmark, Copenhagen. So that's a ski slope. So they designed a ski slope around the waste energy plant so that the residents of the country during winter time they can do skiing and have fun next to the waste energy plant. So that also tells you how safe the plant is. That if they're inviting public to come and do skiing next to it, that tells you the plant is designed according to the highest safety standards. Then there are around 75 units in the US. In Japan, there are around 1,000 units installed already. So the reason why there are 1,000 units in Japan is because of the space constraint. Japan cannot afford to have landfills, so they have more waste to energy plants in Japan. China and South Korea again there are around 120, but it's growing very fast. In India currently we only have 7 installations, but more plants are being not commissioned, but they are studying the option of developing more plants in India. Middle East, there is an operation plant in Qatar. Sharjah and Kuwait, they are right now tendering a plant for construction. In Oman, like I said earlier, we finished the feasibility study and the detailed analysis of 2 plants now waiting tender because of COVID. The tender got postponed to next year. So, what are the technologies that we have? So, I kept saying thermal treatment. So, there are different types of installation. It's not just one type. The common ones are great technology, then there's fluidized bed and rotary kiln. So each can be applied for different types of waste. Each has its advantage and disadvantages. But if your municipal solid waste is not, say, pre-treated, the best option is to go with great. That's why you will see the majority market share across the globe is for great incineration technology. because in most places they don't do pre-treatment of the waste. This is a simple schematic of a waste energy plant. So on the left-hand side, the waste is transported via a truck and it's unloaded onto a waste bunker. There's a crane which grabs the waste and they put it onto a hopper, and then the hopper feeds the waste into a furnace. The furnace heats heats the waste and it heats the boiler. The boiler then converts the water into steam. Steam runs the steam turbine, produce electricity. The gas that results from the incineration of the waste, it's treated. It is sent through a filtration system, a proper air quality treatment system, and then it goes through a chimney. The bottom ash from incineration of the waste is collected and sent for recycling or for disposal. Now I'll show you what it actually looks like. It was a very simple schematic. So this is what a bunker looks like. So it's quite huge. The reason why the bunkers are quite huge and that space is like developed in that way is so the trucks can come and unload the waste onto these bunkers. Usually it's also done as a contingency. So it's not just in time delivery like the Kaizen or the Japanese Kaizen philosophy, because there can be natural disasters. Or something happened, the truck broke down. So you cannot have the plant idle for that period of time. So what you tend to do is you have the bunker capacity for at least 7 days. This is the minimum usually. So it's designed to have an excess capacity of 7 days worth of waste or fuel. Now we're going to fuel concept. Okay, so you need to have sufficient extra capacity. In the event of any disaster, you can rely on the excess from the bunker. Another purpose of having the bunker is if something happens, like suddenly you have 5 trucks coming full of, say, paper waste or food waste, for example. So what tend to happen is you cannot feed it directly onto the hopper because, as I mentioned earlier, each waste component have different characteristics. So you need to homogenize the waste before you feed it into the hopper because, like I said, the thermal output depends on the calorific value of the waste and the quantity that you need. So another purpose of having such a bunker is to mix the waste and homogenize the waste before you load it into the hopper. So this is what a hopper and a chute looks like. And right hand corner, you can see where exactly it's located in the waste management plan. So once you load the waste onto the hopper using the grab crane, it's loaded onto the grate in a systematic manner. It's not immediately all of it goes into the grate, slowly loaded onto the grate so it can achieve complete combustion. Right. So this is what a grate looks like. So grate usually it's kind of like a step. So if the waste comes on top of this particular grate, it moves like this. It keeps moving. It's all burnt by the time it reaches the end of the grate and form it's turned into ash. So air is very important because if you don't provide sufficient air in grate, the waste does not burn. So by the time it reaches the bottom, it's not ash, it's actually the waste itself. So that's why there's different types of air feeding happening. Secondary air injection, there's tertiary air injection, and side walls and the grate is also cool because you don't want it to reach very high temperature and starts clogging the system. So it is a very sophisticated process. So this is what a boiler looks like. Some of you who have experience going to any thermal treatment plants would have noticed that it's very similar to a thermal treatment plant. There is a combustion chamber, there is a steam drum, there's a superheater, there's an economizer. The whole point is you need to achieve a certain steam parameter for running the steam turbine. So that's why the boiler is designed in a way to capture as much as heat as possible from the flue gas and then use it to run the turbine. Now, this is the most sophisticated part of a waste energy plant, the air pollution, the emission control systems. Uh, I would say if the plant costs around 500 million US dollars, the air pollution control system alone costs 200 million US dollars. So you can imagine the sophistication of this particular component because you cannot take chances near burning waste. So the different types of systems which are usually employed in a waste energy plant is a scrubber, that's a cyclone and bag filter for taking out dust, hydrated ammonia for taking out NOx, which is nitrogen oxide, activated carbon for taking out heavy metals, dioxins, and dust. So this is the full schematic, but I don't want to go into detail. I'll show you what the individual components look like. So this is what a DNOx system looks like. So when the flue gas is generated, as you know, the air is made of a significant percentage of nitrogen. So at 700, sorry, 700, 800 degrees Celsius, the nitrogen in the waste as well as the air gets converted to nitrogen dioxide. So you cannot let it escape into the environment because it will combine with the atmospheric moisture and then can convert it to nitric acid. One of the reasons why we had acid rains is the nitric acid and sulfuric acid as generated from such plants. So what you tend to do is you denox it using ammonia. So when you sprinkle ammonia with water, it converts the NOx back to ammonia. So and nitrogen. So this is a system that's typically employed in waste energy plants across the globe. And this is a filter system. Like I said, this is usually done for capturing the dust which is generated from the flue gas. So it's a very sophisticated unit. You can see the size on top right hand corner. Sorry, the top left hand corner. You can see a man. So you can see how big the filters are for taking out as much as dust as possible from the flue gas. So what are the limits that we need to follow? So the Indian regulation that came out in 2016. So these are the emission limits that are set by the government, which any waste energy plant in India have to abide by. So just I did a small comparison with European Union as well. You can see in some areas we are a bit relaxed, in some areas we are a bit more stringent than Europe. In the case of sulfur dioxide, when it comes to NOx, we are a bit more relaxed. Heavy metals, mercury and dioxins, we are on par. So it is up to the country to decide what is the emission limits, depending on various factors like the environmental impact assessment done, the effect of such gas on the environment. So a lot of study has gone into for the government to make such a decision on what should be the emission limits. So how does the financial looks like? So I did this as a case study. So this is an example from Kerala where they were planning to develop a waste energy plant. So there's an SPV formed between the technology supplier, there's local partner, there's an international financing because when you say plant costs something like 100 million US dollars, it's not something that you can source easily from the local market. So you also look for international financing partners for such plants. There's an international operator because we need an experienced operator for operating such plants. So there's an SPV form, which is a special purpose vehicle. Developed as a consortium of this particular group of entities for designing, financing, building, owning, operating, and then finally transferring the plant to the government. The government commits from the left hand side. So the government gives them land free of charge for the period of concession. Then they give a pollution objection certificate, and the KSEB or the local electricity board the grid operator, they sign a power purchase agreement on the plant for the period of duration of the contract. So they decide, they negotiate the price of the electricity, the unit of electricity. Usually there's also another scenario where the plant gets paid also from accepting the waste as a fuel. So for 1 ton of waste I receive onto the plant, I expect to receive so much rupees per ton. So, but in the scenario, the case study in Kerala, they didn't had that particular scenario. It was all from the power purchase from the KCB. So, is this an efficient system? You might ask me. I would say I have my apprehensions because recovering electricity only is not the most efficient plan. So you can see in this particular diagram, I did a comparison of two particular scenario where there's only electricity and there is cogeneration. Cogeneration means electricity and heat. Heat means it can be steam, it can be hot water. So it depends. So this is the two comparison that which I did. So for a plant that produces only electricity, the maximum efficiency I'm looking at is 20% because it uses a condensing turbine, which there's a lot of heat which is lost in the environment. But your priority is producing electricity, so that plants tend to be less efficient. But when you go for cogeneration, what tend to happen is the electricity output of the plant reduces because you're sacrificing the electricity. Some of the heat gets utilized for the thermal application. So when you add them, the thermal efficiency and the electricity efficiency, what tend to happen is the energy output is around 80%. So the plant is more efficient than when you're looking at electricity only. So what can you do with this heat? Like when I presented in South Africa, someone asked me this question, like, we keep talking about heat, steam, like where can I use it? So these are some examples where for industries that require so much steam. So fertilizer industries require a lot of steam, petrochemical industries require a lot of steam, paper mills require a lot of steam. So there are industries in India that require a lot of steam, so or heat. So it depends on how you co-locate your plant next to such an industry. So how does it impact the economics? So this is again example from this is an example from a plant operating in Austria. It's a 40 megawatt plant with an annual capacity of 100,000 tons. They receive, like I said earlier, like they get some money from the waste tipping, which means when I receive 1 ton of waste, I expect to get paid certain amount of money. So annually they get 5 million euros from the municipality over there for accepting the waste. The waste then gets incinerated and produces some form of energy. I'm not saying heat or electricity, some form of energy. So you can see the comparison. So without an off-taker of heat, the plant produces more electricity, which sells to the grid. The annual income is only 1.5 million euro per annum. Okay, but if the plant was able to sell heat to the local industry, so why should the local industry pay for the steam? Because they save on the gas or any other fossil fuel which they're burning for producing steam. So they pay for the steam. So you can see the annual income for that particular plant becomes 6 million instead of 1.5 million. So that's how it impacts also not just the efficiency but also the income of the plant. So is it done anywhere? I mean, it keeps talking about examples. So I happened to visit such a plant in Austria, in Lenzing. This plant is co-located next to an industry that generates, it's a textile industry that generates rayon. It's a kind of textile that's used as a replacement for cotton. So in that plant, it is not just co-located for the steam purpose. There's three purposes for co-locating the plant. One is obviously the steam that they generate. It can be fed into the textile manufacturing unit. Second is the textile manufacturing unit produces a lot of hydrogen sulfide gas, which traditionally needed to be sent to the environment through the stack. So that gas, now they are feeding it back into the furnace process. They thermally treat it in the waste energy plant, so they don't have an issue with hydrogen sulfide. It gets converted to sulfur dioxide, which is captured using the scrubber system, which I explained earlier. And third is landfilling. So the industry generates certain types of industrial waste, which is fed into the waste energy plant. So they recover energy from the industrial waste. So this is the schematic of this particular plant, where like I said, the polluted air from the plant is sent into the furnace. The furnace produces steam, which is sent to the paper production, the pulp, into the fiber production unit. The sewage sludge and other waste from the local municipality is sent as a fuel also into the furnace, which generates enough steam for the unit. So this plant has been operating since 1998, and they treat around 1,000 tons of waste per day. And this is a mix in the pie chart. You can see the different types of waste. Different types of waste they use for incineration in this particular plant. So, what are the factors that you need to consider while selecting the site? Obviously, you need to have year-round heat requirement. Then, like in the case of lensing, if it is possible to reduce the environmental stress, like if there's a pollutant being emitted from like sulfur dioxide or hydrogen sulfide, you can channel it into such a plant, thereby reducing overall environmental stress from such a plant. Spatial planning is very important. So you need to see if you can co-locate it if the plant is located in any recreational or protected area. So as much as possible, try to locate the plant away from such protected zones. Then the meteorological and topographical condition, that's very important when you select the site. Good transport links. This is very important because on the right hand side you can see a picture of a bay, which is a plastic covering for the waste. Usually it's done for hay. In Europe, they generate this hay. Even North India places they have this hay is used for animal feed. So that instead of hay, right now we are looking at waste. They coat the waste. They cover the waste using this particular bale. They bale it and they load it and they ship it from Italy to Austria for treatment in a waste energy plant. So if you have good links, the waste energy plant is co-located. You can, in the long term, you can strategically, source the waste from different locations. Then accessing infrastructure, like I said, like transportation, laboratory, firefighting systems, um, then uh, then technical installations. Like if there's already industry that has a turbine or generator installed, then that's the best option. And then you need an experienced team for doing the operation and maintenance of such a plant. Coming to the conclusion of my presentation, like I said, there is no off-the-shelf solution for diverting the waste. You cannot just copy and paste. You need to develop an integrated solution that's best fit for your regional, national targets and regulations. You should always look for a solution that has the least ecological impact. Always look at the waste hierarchy with emphasis on waste segregation source and reuse of material for waste purposes, like I mentioned, from the economic perspective and also for from the treatment perspective, like the always you need to prefer the segregation and reuse. Yeah, so select an appropriate site. Always select a site by studying the local industries, whether they have an energy demand or upcoming energy demand. Like if one of the steam boilers are nearing the end of its life and it needs to be replaced. So can you co-locate a waste energy plant next to that industry? They can use the energy from this plant. And yeah, like I said, it results in higher efficiency and also revenue. And always you need to raise awareness and education for teachers, managers, policymakers when it comes to waste energy to reduce the NIMBY syndrome. What is NIMBY is not in my backyard. It's a commonly used term in waste management sector. Like people want good solutions, want the state-of-the-art solution, but it's not exactly in my backyard. Somewhere far away from my house, far away from my neighborhood, I would rather have a state-of-the-art facility. So unless you are educated, you always tend to be skeptical about any waste energy solution. So it's also needed to raise the awareness for accepting the solution. So thank you so much for listening to my presentation. I hand over the presentation to the chairman. Hello? Hello, Alex? Hello, Alex? Jobina?
Hello, thank you, sir.
So can you conclude if you don't mind?
Yes, sir. Just a minute.
Yes, I can. Okay. Okay. Okay, this is a very challenging question. So segregation, it's a community level requirement. You cannot just, I mean, yeah, you can start from your households. They can segregate, but there need to be some supporting systems in place to continue. Like there's a situation. I'll give you an example of what happened. There was a drive that happened in St. Teresa's College in Cochin, where the dean of economics department wanted all students to segregation of plastic and bring it to the university. So they all did it, and they were coordinating with the local municipality in collecting this waste and taking it separately to a treatment facility. What happened was the common municipal collection truck came, took all the waste, mixed it with the municipal solid waste, and went away. So that is kind of discouraging when you do segregation. You took the care in segregating the waste, and then there is no separate collection or treatment happening. So when you talk about reuse, um, obviously adopting or utilizing less plastic bags that's the easy option that is available for all of us. Like if you can use cotton bags when you do shopping, or other option is when you go, yeah, exactly. So that's the most common option which is available for reuse. Like when I even here in Oman, like we use a cotton or jute bag. We go for shopping. So we found out that the amount of plastic bags that we generate is significantly reduced, or the plastic generated. And there are a lot of these shops which are coming up where you can go with your own. Like I was in Auroville and Pondicherry, where they have shops where they ask you to bring your own bottles when you want to fill oil, or if you want to buy some milk. So they give you glass bottles. So this kind of initiatives can be taken on a community level if you can discuss with the people over there. But again, it's, yeah, I mean, you can start at home, but you need to also encourage the local society to also adopt uh, you know, systems where you produce less waste. I think that kind of answers the segregation and reuse option. Any other questions? I think I answered that question. So one, you need to understand the waste. What is the quantity available? When you invite an international waste to energy developer to come set up a plant, they look at certain things. One is the quantity assured. Second, what is the characteristics of this waste? Third, what is the price with which the electricity is purchased by the government onto the grid? Or if there's an industry that can offtake the heat. So all these factors play a role in developing a waste to energy plant. But when it comes to organic waste, if it's okay, when I talk about waste to energy, I talk about waste to electricity, thermal treatment waste. When you're talking about a biogas plant, on the other hand, what they look out for is the waste contaminated with organic waste, because it requires pre-treatment if it's contaminated. So that waste, what's the volume, what type of waste it is, because each fraction, like for example, vegetable peelings tend to generate different percentage of biogas in comparison to, let's say, a slaughterhouse waste. Understand? So, what is the percentage of organic waste? They study that, and how much gas can they extract, process from such a biogas plant. So it depends on what type of technology you're looking at. But basically, it all boils down to the nature of the waste, the quantity of the waste, the assurance, the contract period, then the fees, like I said, how much fees is the government willing to pay per ton for the waste energy plant for accepting this particular waste, and how much energy you can recover. What is the price at which the government is purchasing electricity? It might be gas itself in certain cases, or it will be electricity or heat. So that's how we decide whether you need to go with the waste energy or not. I hope that answers the question. Yeah, sure. No problem. Okay. Okay. I mean, that's a very interesting question. When I did the study in the Panchayat level, they asked the same question. Does it make sense for us to develop a waste energy plant? So my answer was not really. So we need to have rural areas, the quantity of waste is less. So the option of developing waste energy plant is not easy. Unless it's a community level biogas plant. But then again, you need to have a possible utilization for this particular gas. Like for example, you can see a lot of these biogas plants now being developed on a community level, say in schools and colleges, where they can use this gas for cooking purposes. So they can reduce their dependence on natural gas by having a co-located biogas plant where the waste from the locality and also the centralized kitchen can be sent for producing biogas plants. But apart from that, for rural areas, mostly the preferred option is to reduce the cost or impact associated with transportation. So you saw in my slide, at least 60 to 70% of the waste is organic. The best option is always to treat the organic waste at source by having a home composting unit or a community level biogas plant. So you reduce your problem by 70%. Now the remaining fraction, what can you do? So plastics is always a headache. I will be honest with you. Paper, you can always sell it to a local collector. Clean plastic again, metal fraction, yes. So plastic bags end up becoming a headache. So the municipality, the panchayat, which where I work for, had the same issue. Like at the end, we come down to that plastic fraction. What can we do? So I take the whole aspect of the government's introducing the ban on single-use plastic from next year or this year, I believe. I take it in a positive way because we as India, we still haven't developed a solution for treating this particular nasty fraction. Although it's high in calorific value, at a panchayat level or a rural level, it remains a big headache because you cannot do much with it. In Tamil Nadu, for example, I've seen cases where they're shedding a lot of the plastic and using for road construction process. That's an option, but again, when you go rural level, there might not be so much roads being constructed. So the cost of transporting this waste, baling it, storing it, and sending it again adds cost. So my suggestion is always you can reduce the plastic bags. Bottles again you can somehow set it back into the grid for as pet flakes or recyclable fractions into the grid. But the problem is with bags, that option is not much available. But if you are in a city level, yes, there are options that you can explore. I hope that answers the question. Hello? Thank you. Thank you so much.
Every part of the world is rolling out solutions to battle carbon emissions Energy from waste is a hot topic at the minute to fight against climate change. So its role in promoting longer-term environmental responsibility is only going to get more significant. Good evening, everyone. I deem it a great honor to propose the vote of thanks to all who have helped us in making this webinar such a resounding success. First of all, I would like to propose hearty vote of thanks to our management, Hindustan College of Engineering and Technology, Coimbatore, for giving us an opportunity to conduct this webinar on waste to energy concepts and its role in waste diversion. I would like to thank the resource person, Mr. Anup Taliat, Business Development Oman Environmental Services Holding Company, BIA, for gracing today's webinar. Thank you, sir, for making an excellent presentation emphasizing the importance of waste to energy and throwing light on the diverse technologies of recovering energy from waste. I would like to express my profound gratitude to our beloved HOD, Dr. Akil Kannan, for her moral support and guidance. I'm happy to express word of thanks to our organizing committee, the faculty who have made this webinar a grand success. I thank all the students of the Civil Engineering Department and all the participants of other institutions who have participated overwhelmingly in making this webinar successful. Thank you, everyone.
Thank you, everyone. Thank you. Thank you so much. Bye.
எப்பதான் போய் கோத்துருவாரு போய் பட்ஜெட் முடிச்சுன்னு சொல்லப்பா